Hello, welcome to Lecture 21 of Electrical Circuits 1. Beginning of lecture today, we're going to talk about what we talked about at the end of the last lecture. We're going to rediscuss the series RLC circuit response equations and the parallel RLC circuit response equation. Next, we will look at these in the context of an overall general second-order circuit response. And we'll start emphasizing the natural response. We'll defer the forced response of second-order circuits until later. Once we've developed the form of the natural response for a second-order circuit, we'll need to talk a little bit about sinusoidal signals. As I said last time, the natural response of a second-order circuit can oscillate. So we'll have signals that look sinusoidal in nature. We will deal with them in terms of complex exponentials. So we'll spend a fair amount of time this lecture talking about sinusoidal signals, complex exponentials, and a quick review of complex numbers. The related material in the educational modules is in sections 2.5.2 and 2.5.3. Okay, in lecture 20, we developed the governing differential equations for series and parallel RLC circuits. I just want to summarize those results here before we continue on. For a series RLC circuit, we have a resistor, capacitor, and an inductor placed in series. Since they are in series, they all carry the same current, I of t. When we derive the governing relationship relating I of t to the source voltage V sub s of t, we developed an equation that was dVs by dt is equal to L times the second derivative of I with respect to time plus R times the first derivative of I with respect to time plus 1 over C times the current itself. For a parallel RLC circuit, the parallel elements all have the same voltage difference. The governing differential equation that related voltage to our current source for this circuit was the derivative of the source current with respect to time was equal to C times the second derivative of voltage with respect to time plus 1 over R times the first derivative of voltage with respect to time plus 1 over L times the voltage itself. Notice, both of these circuits have second-order derivatives in their input-output equation. They have two independent energy storage elements. They each have an inductor and a capacitor. So two independent energy storage elements corresponds to a second-order differential equation, which means the circuit is overall second order. Now, before I go on with the rest of the lecture, I want to look for a common form between the two of these. I'm going to write these in a kind of standard form ultimately. If I divide through by the leading coefficient on the second derivative term, I get a 1 over L dVs by dt is equal to d squared I dt squared plus R over L di by dt plus 1 over LCI. Likewise, if I divide out the leading coefficient on the second derivative term in this equation, I get a 1 over C times dis dt is equal to d squared V by dt squared plus 1 over RC dV by dt plus 1 over LC times the voltage. These equations both essentially have the same form. We have a 1 in front of the highest order derivative. We have some coefficient in front of the first order derivative and some other coefficient in front of the 0th order derivative. Those are equal to some forcing function. Okay, so I'm going to write these equations in the same form on this next slide, which will allow me to provide some physical insight into what these particular coefficients are doing to my overall circuit response. So what I want to do is write a general second-order input-output differential equation. The way I'm going to write it is in this form. My output is y of t, my input is u of t. This is some function that is applied to the circuit or the system. This is the signal that I'm interested in determining. I have a 1 in front of the highest order derivative. So I have d squared y dt squared plus 2 times zeta omega n times dy dt plus omega n squared y is equal to u of t. Both of my previous equations can be written in this form. Okay, the reason I want to write it in this form is that zeta, which I tend to just call squiggle because it's too much work to remember the Greek letter, and omega n have physical significance in terms of the circuit's response. If I know squiggle and omega n, I can infer something about the way the circuit is going to respond without actually solving the second-order differential equation. Second-order differential equations become increasingly difficult to solve. In general, what I would like to do is get a feeling for what the solution looks like without actually going to the trouble of solving them. Now, squiggle and omega n have special names. They have special meanings. Squiggle is called the damping ratio. Okay? Omega n is the natural frequency of the system. Both of these are non-negative numbers. Okay? And later on, when we take a look at the form of the solution here, we can start to see what effect these have on the solution itself without actually dealing with the details of solving each individual second-order differential equation that we generate. Okay, let's start looking at the form of the solution of this differential equation. All differential equations, their solutions are the sum of a homogeneous or unforced solution and a particular or forced solution. So y of t is still the sum of y sub h of t, the homogeneous solution, plus y sub p of t, which is the particular solution. Now, the same way we did with first-order circuits, I'm going to worry about the homogeneous solution first. Okay? So for the homogeneous solution, we have no forcing function, so our differential equation, d squared yh dt plus 2 squiggle omega n dyh dt plus omega n squared yh is equal to 0. Solving this will give us the homogeneous solution y sub h of t. Let's determine the form of the homogeneous solution or the natural response of the system. Now, at one point for first-order systems, we said that one common way to solve differential equations is to just guess the solution. The solution will always be of the form e to the something times t for linear, constant coefficient, ordinary differential equations. So for this second-order system, we are still going to assume the form of the solution, and we'll assume that the homogeneous solution is of the form e to the st. Okay? Now, if we plug this into our original differential equation, set it equal to 0, we'll get this condition on s. So s squared plus 2 squiggle omega n s plus omega n squared will have to be 0. We can solve this equation for s. It's a quadratic equation. S has two possible values that will satisfy this equation. So the two values are negative of squiggle omega n plus or minus omega n times the square root of squiggle squared minus 1. So the first solution is negative squiggle omega n plus this term. The other solution is negative squiggle omega n minus this term. Now, our overall solution has to reflect both possibilities. I'll get into that in the next slide. Okay, our overall homogeneous solution has to reflect the fact that we have two possible solutions. So our overall solution is going to be some linear combination of the two individual solutions. So it's some unknown constant k1 times e to the s1t plus some unknown constant times e to the s2t. If I plug in s1 and s2 from above, I get k1 e to the minus squiggle omega n plus omega n times the square root of squiggle squared minus 1 times t plus k2 times e to the minus squiggle omega n minus, right, plus and minus here give me my two solutions, omega n square root of squiggle squared minus 1 times t. Now we have two unknown constants. Okay? When we did first order differential equations, we had one unknown constant. We needed one initial condition. Now that we have two things that we need to determine about the natural response, we need two initial conditions. Generally, these are, first, the value of the homogeneous solution at time t equals 0 is some value y sub 0. Second, the derivative of the homogeneous solution with respect to time at t equals 0 is some number y prime sub 0. So we're given the value of the function at t equals 0 and the derivative of the function at t equals 0. We will use those to find k1 and k2. Now let's take a look at the form of this solution again. Now both of the terms that we're multiplying k1 and k2 had this e to the minus squiggle omega nt in them. I can pull that out, factor it out, and just retain the k1 times e to this plus k2 e to the minus this. Okay, remember that omega n and squiggle are both positive values. Okay, they can't be negative physically. You cannot have a negative value of squiggle or a negative value of omega n. If the damping ratio is bigger than 1, okay, this is a positive number. This guy here, because of this sign, is a negative number. So this is an e to the positive value. This is a growing exponential. So this term here grows exponentially. This guy here decays exponentially. Now, this guy here gives us some problems, okay? We do not want to start up a system from some set of initial conditions and have the output grow exponentially. Okay, so far we've only talked about passive type circuits, so there's no energy that can cause this output to go to infinity. Okay, luckily this guy here is saving us. This one here also decays exponentially. And if squiggle is a positive number, the square root of squiggle squared minus 1 is always less than squiggle. So this guy will decay faster than this one can grow. So the combination of these two must decay exponentially. Now, if squiggle is really, really large, this may grow almost as fast as this decays, and the overall result may decay very slowly, but it's going to decay. The natural response will go to 0. That was our physical justification when we were doing first-order systems. The natural response has to go to 0. This guy decays exponentially. He's multiplied by something else that decays exponentially. This term here is going to decay, and it can decay rather rapidly. Okay, so you have one term that is decaying exponentially, possibly very slowly, and another term that is decaying exponentially, possibly very fast. And the overall solution is a sum of those decaying exponentials. Now, what happens if squiggle, the damping ratio, is less than 1? If squiggle is less than 1, the square root of squiggle squared minus 1 is an imaginary number. So we have e to some imaginary value. We don't necessarily know how to deal with that. E to an imaginary value is called a complex exponential. I'm going to spend quite a while talking about complex exponentials and how to interpret this solution under this condition where the damping ratio is less than 1. Okay, I want to talk about complex exponentials. But in order to talk about complex exponentials, I first need to talk about sinusoids. Complex exponentials and sinusoids are very closely tied to one another. In fact, they're really the same thing. Now, I'll assume that you're a little familiar with sinusoids, so I'll just do a quick review of the basics of sinusoidal functions. Our general form of a sinusoidal function for this class will be v of t is some number v sub p times cosine of omega t plus a phase angle theta. We will always use cosines in this class for reasons that I will explain later. This covers the case of sines because a phase-shifted cosine can be used to represent a sine. Okay, there is no loss of generality just by emphasizing cosines. Okay, v sub p is the 0 to peak value of the sinusoid. And I'll explain these graphically in the next slide. Omega is the angular or radian frequency. Okay, the units of this have to be radians per second. Any number inside the argument of a sinusoid has to be dimensionless. Okay, radians have no dimensions, so if I take radians per second, multiply them by seconds, I get something that has no dimension. I'm okay with putting that in this argument. Okay, that is important. You have to use radians per second for omega. Theta is the phase angle. Okay, now in this class I will use either degrees or radians sort of arbitrarily. I don't care which one you use. Mathematically, theta needs to be in radians. Okay? Now, people use degrees, especially engineers like to use degrees, so we'll use that unit a lot, but keep in mind that this really needs to be converted to radians so that your units are consistent between omega t and theta. Okay? Go to the next slide, look at a graphical depiction of this, and show these on that slide. Okay, here's my phase-shifted cosine function. It can be generated from the equation on the previous slide. V sub p gives me the peak value of this function. So V sub p is this envelope that the peaks hit. The cosine also goes through negative v sub p. So the peak-to-peak amplitude is twice v sub p. The 0 to peak amplitude is v sub p. Now, the frequency of this sinusoid graphically is depicted by a time period capital T. Okay? T is the period. It is in seconds. Now, you will see a lot of people using f for frequency to describe the frequency of these sinusoids. Generally, when they're talking about frequency rather than omega, radian frequency, the units are cycles per second. That's abbreviated as Hz for hertz. Okay? It is the number of cycles that this sinusoid goes through in 1 second. That is numerically just the inverse of capital T. Okay? Now, omega on our previous slide is not quite the same as f. Okay? Omega, radian frequency, goes through 2 pi radians in 1 period. Okay? Therefore, omega is 2 pi times f, so omega is 2 pi over t. Now, one of the main problems that students have at the sophomore level is to make sure that they're using the right value for the argument in their sinusoid. We're always going to want to use radians. Unfortunately, hertz is probably a more common unit to use in the laboratory. If you have a function generator or something, you will be generating sinusoids of X number of hertz. When you're doing analysis on those sinusoids, you'll need to convert that to radians per second. The phase angle theta, okay, it allows us to shift this sinusoid in time. Remember when we did unit step functions, we had u0 of t minus a, where the a allowed us to shift to some time period on the time axis. The theta does the same process. So theta is phase. A negative phase shifts the sinusoid to the right. And in fact, the phase here is going to be minus theta over omega. This gives me a time at which the cosine's peak is represented on the time axis. Okay? So omega gives me the rate at which this is oscillating. Vp gives me how high the sinusoid is, and theta or phase tells me where this sinusoid is along the time axis. Okay, remember what I want to talk about is complex exponentials. I said that in order to discuss complex exponentials, I need to refer to sinusoids a little bit, which I just did. In order to understand complex exponentials, you also need to understand complex numbers. So now I'm going to do a brief review of complex numbers. This is another topic that you should have some experience in. So, complex numbers have both a real and an imaginary part. A complex number, capital A, is little a plus j times little b, where little a and little b are just numbers. J is square root of -1. In your physics class, you probably used lowercase I as the square root of -1. Electrical engineers generally use I for current. Therefore, we switch over to using J for square root of -1. Graphically, we can represent this in a complex plane which has some direction on the real axis and some direction on the imaginary axis. So A is the distance on a real axis, B is a distance on an imaginary axis. This number here, A, is A plus J times B. Notice B is the imaginary part of A. That is represented by IM, generally with curly brackets, A. So the imaginary part of A is B, and little a is the real part of the complex number A. Okay? Notice one thing that gets people confused. The imaginary part of A does not contain this J. Okay? J is telling me which of these is imaginary. The imaginary part is not that J. B is the imaginary part. In order to use complex numbers effectively, you want to be able to use both polar coordinates and rectangular coordinates. Now, our previous representation and plot of a complex number was on rectangular or Cartesian coordinates. We had essentially an XY coordinate system that gave the real and imaginary parts. Now, any planar location can be represented by an XY plane or rectangular coordinates or polar coordinates. In polar coordinates, my complex number A has some magnitude, capital A, and a phase angle, theta sub A. That's represented here. This is still A is equal to A plus J times B. In rectangular coordinates, I have a real part A and an imaginary part B. This point here can also be represented in polar coordinates as a distance from the origin, which is magnitude of A, and an angle from the real axis, which is theta sub A. The angle is always taken positive counterclockwise from the real axis in the direction shown and from this reference shown. Numerically, relating polar and rectangular coordinates, the magnitude of A by the Pythagorean theorem is this is just a right triangle. The hypotenuse is the square root of A squared plus B squared. Trigonometrically, this angle is the arctangent, okay? The opposite over the adjacent is the tangent of this angle. So this angle is the arctangent of B over A. Okay, now I can actually start talking a little bit about complex exponentials. Complex exponentials are a way to represent a complex number in polar coordinates. So if we have a polar coordinate representation of a complex number, magnitude of A with an angle of theta sub A, we generally represent that as a complex exponential with the magnitude of A multiplying e to the j theta sub A. So the angle of the polar coordinate goes into the power of the exponential, the j tells us to interpret that as an angle in the complex plane. So, comparing these two, e to the j theta sub a is therefore essentially defined as something with a magnitude of 1 and an angle of theta sub a. So graphically, okay, e to the j theta sub a is a unit distance away from the origin, and it is an angle theta sub a from the real axis. Okay? So we're now representing a complex number using complex exponentials. Now let's take a look at using complex exponentials to represent a time-varying function. Okay? Remember, Euler's identity. E to the j theta sub a is cosine of theta sub a plus j times sine of theta sub a. Graphically, okay, if I have e to the j theta sub a here, cosine of theta sub a, okay, is the adjacent side over the length. The length is 1. So this distance, the projection of this point onto the real axis, is cosine of theta sub a. This projection of this point onto the y-axis, opposite over hypotenuse is sine. If the hypotenuse is 1, the opposite leg of this triangle is just sine of theta sub a. So, complex exponentials are intrinsically tied up with cosines and sines. What we're going to do next is allow this coefficient here to vary with time so that we can get a cosine of omega t by making this a j omega t. So as I mentioned previously, we're now going to take this concept of a complex number being represented as a sine or a cosine, generalize that to a function in the complex plane, which is generating a sinusoidal function with time. So what we're going to do is think in terms of a little unit vector. This is length 1, and I'm going to let this vector rotate in the complex plane. So its angle here is a function of time. And in fact, what I'm going to do is make this angle a radian frequency times a function of time. So this guy is spinning around here. The tip of this vector is moving around this unit circle, and the value of omega tells me how fast this spins around the origin. Now I'm going to use this omega t in a complex exponential. So I have e to the plus minus j omega t, and using Euler's identity, that becomes cosine of what multiplies the j here, so it's cosine of omega t plus or minus. Okay, if this is a positive number, it's a plus here. If this is a negative number, it's a minus here. J times sine of what multiplies j in this exponent. Okay, so e to the plus minus j omega t is cosine omega t plus j sine omega t. So the cosine is still the projection of this tip of this vector onto the real axis. So as this thing is spinning around, the projection of this vector onto the real axis is going backwards and forwards here as time progresses. So at time t equals 0, the tip of this vector is at this point. My cosine is projected down. It is 1. As this spins up here, this point moves to the left. I move on my sinusoid this way until I get all the way over to the left hand of the circle, at which point I come down here, my projection starts to move back this direction, and the tip of this vector, if I project it onto the real axis, traces out cosine of omega t. Okay, so I can use this guy here to represent sinusoidally varying functions. Now, why would I want to do that? Okay, why do I want to do this? Okay, complex exponentials, as I said previously, can be used to represent sinusoidal signals. Okay, we saw that the projection of that complex exponential as it varies with time becomes a cosine function. Okay, and what we're trying to get to is representing our cosine omega t type function. Remember, our sinusoidal signal was v of t is equal to v sub p cosine omega t plus phi. Analysis, mathematics, is almost invariably easier with complex exponentials than with sines and cosines. When I assumed my form of my solution, I assumed that my solution was of the form e to the st. Taking the second derivative of e to the st was not difficult. Okay? If I had assumed the form of the solution was v sub p times cosine of omega t plus theta, the second derivative of that is kind of painful to deal with. So we like to work with complex exponentials. Okay? As long as we have positive and negative powers on our complex exponentials, and if the powers are the same, those will represent a pure sinusoid. Okay? If we rewrite Euler's identity, cosine omega t is e to the j omega t plus e to the minus j omega t over 2. Likewise, sine omega t is e to the j omega t minus e to the minus j omega t over 2 times j. We can recombine these complex exponentials to create sinusoids. Okay? So if we do our analysis in terms of complex exponentials, we can always interpret those in terms of sinusoids that vary with time. That makes life extremely easy as long as we're comfortable with the idea of thinking of complex exponentials as things that oscillate with time. Okay, now we have the tools to go back and look at our previous result and interpret it in the case that we didn't understand possibly before. Now, when we looked at this before, we said, okay, if the damping ratio is bigger than 1, these terms here are either growing or decaying exponentials. Even if this guy is growing with time, this guy is going to cause the overall solution to consist of decaying exponentials. No problem there. Where we ran into trouble was that if the damping ratio was less than 1, this became an imaginary number, this became an imaginary number. We had complex exponentials. Okay? Now we kind of understand more about what complex exponentials are. So we have some imaginary number here. We have a negative of the same imaginary number here. These guys can be combined to form sines and cosines. Okay, we're going to look at a complex exponential and say, oh, that looks like an oscillating signal. Okay? So now if the damping ratio is less than 1, our solution is going to contain sines and cosines in here. These sines and cosines will be multiplied by a decaying exponential. So what we'll have are sines and cosines that decay with time. Okay? So they'll be sinusoidal, but they'll die out with time the way we would expect to happen if we have actual damping in the system. Now, one special case, if the damping ratio is exactly 1, okay, this guy here becomes 0, e to the 0 is 1. This guy here becomes 0. E to the 0 is 1. We have k1 plus k2. This term in here becomes a constant. This guy here is going to be a decaying exponential. So if the damping ratio is exactly 1, we have a constant times a single decaying exponential. So the result is going to decay exponentially if the damping ratio is 1. However, it has one special feature. This term here that's growing with time has gone away. Okay, this term here is growing with time. It was making us potentially decay to 0 very slowly. Okay, so this guy decays exponentially, but he decays faster than any solution which has a damping ratio bigger than 1. Okay? And in fact, these characteristics are used to categorize second-order systems into 3 basic categories. Okay, it's common to categorize second-order systems by their damping ratio. That's one of the reasons that we wrote that original second-order differential equation in its general form, which included squiggle and omega n. Because now we can take a look at the number for squiggle alone and get some idea as to what the natural response is going to look like without necessarily going to the trouble of solving the differential equation. So if the damping ratio is bigger than 1, the system is said to be overdamped. Okay, this is the case in which we had growing and decaying exponentials inside those square brackets, and the overall response was the result of a growing exponential multiplied by a decaying exponential, and then the product of two decaying exponentials. So we had a response that consists of a pair of decaying exponentials. One of those may decay very slowly if the damping ratio is large. Thus, if the damping ratio is really large, it may take a long time for our initial condition to die out if the system is overdamped. If the damping ratio is less than 1, the system is said to be underdamped. In that case, inside the square brackets, we had complex exponentials which correspond to signals that oscillate with time. So the response is going to oscillate. As I mentioned earlier, sometimes second-order systems will overshoot when they respond. Okay? This is considered to be an underdamped system. Now, in the special case where the damping ratio is exactly 1, the system is said to be critically damped. Okay? The response is a decaying exponential, the way it is for squiggle greater than 1, but it decays faster than any overdamped version of the system. One further comment on underdamped system responses. Now remember, this comment only applies to underdamped systems. Squiggle has to be less than 1. There have to be oscillations in the response. So for this particular case, this term here contains complex exponentials, and there will be oscillations associated with that. This term here will be negative. We can replace this with the square root of 1 minus squiggle squared times j. So we have an e to the j omega n times the square root of 1 minus squiggle squared. This takes the place of our e to the j omega t. Okay? So the sines and cosines that result from this combination of complex exponentials will have some frequency, which is called the damped natural frequency. It is abbreviated as omega sub d. The damped natural frequency, omega sub d, is this omega n times the square root of 1 minus squiggle squared, because we pulled the j out in order to account for the fact that these are oscillating. So now we see why we used omega n in our original differential equation, because the combination of omega n and squiggle can give us an idea as to what our oscillation frequencies are that we're going to see in the output response of the circuit. So squiggle can tell us how much damping we've got. Omega n can give us a feeling for how rapidly it's going to oscillate if it's an underdamped system. So for second-order systems, I'm going to primarily rely upon these types of observations to get a feeling for what the response should look like. For a second-order system, I will typically use a computer or numerical methods to actually get an exact solution rather than solving the second-order differential equation by hand. But I'll want to be able to check that and see if that solution makes sense. So I'm going to use some of these facts to do sanity checks on my results. This concludes lecture 21. In this lecture, we emphasized looking at the response of general second-order systems. Okay, we're going to write the differential equation governing the system in terms of the damping ratio of the system and the natural frequency of the system. Okay, that'll give us an idea of what the response should look like. Next time around, we'll do some more examples of second-order electrical circuits. After we've written the differential equations governing those circuits, we can get a feeling for what the solution looks like using the tools provided in this lecture.